Before I get started on today's lecture, I just wanted to review some things from last time just to get the equations right. This is the drift current of holes, the drift current of electrons. These values are not set in stone. They can change depending on how you dope your material and the temperature of the material, but these are good values for the mobility of holes and electrons. The current of holes and the current of electrons along with the charge of an electron. So those are some good equations to have on hand. The current density of holes. This is kind of a weird one because we usually think of current, not current density, and the current density of electrons. And just notice on this one, because the current density and the drift current of the electrons both have a negative, when we put it into current density, it becomes a positive. Okay? And that means they both contribute to the same direction of current if we have the same electric field. The electric field pushes the electrons the opposite way of the holes. But to combine, they move charge the same direction. So that's the combined rho L over A, knowing sigma and rho as far as the conductivity and the resistivity of silicon. Resistivity of silicon in particular is this equation here, and I think that's about where we stopped. We may have done diffusion current at the very end of that one, but I think that's where we're going to start right now. Diffusion current, and we'll do this over here on the whiteboard. Diffusion current on this, on our is caused by unevenly distributed dopants. And so if we took a block of dopant, sorry, those are plus signs, a block of silicon, and unevenly distributed the charge throughout here to where this is X, and then we also knew that this, the amount of positive the whole dopants dropped off like this. What this would do is it would unevenly push electrons one way or the other. In other words, this is going to attract electrons because we put positive dopants in there. And so if we just took a snapshot before we let in electrons and let them out, we would see that the electrons would want to go this way. Okay, we'd just for a second want to do this, and if we were to dope it with electrons, so an N-type material, we'd see that. And that's why when we look at these equations in particular, what we can see is we see this is the derivative of that. In other words, the current is with respect a derivative with respect to distance. Okay, and so there is some diffusion, but it doesn't last. It just goes. There's also these defined variables dp and dn. And notice that these have similar ratios to them, if we were to go back up, of these for P and N. It's for the same reason. These are specific to silicon, and I believe that they can change. And the interesting relationship is if we do take those ratios, they're equal to each other, first of all. And so because the dN and dP can change, so can the mu n and mu p. Not very much. They're going to stay in that category for silicon. We also get thermal voltage. And just a reminder on thermal voltage, KT over Q is the thermal voltage, Boltzmann's constant, temperature, charge of an electron. And this was the smaller number of Boltzmann's constant. In other equations that we've used, the Boltzmann's constant has been the other one. And of course, the junction voltage is something new right now. But so we have two things that can push current. We can push current by. I'm sure that was really loud. We can push current by having an unevenly distributed material. It's kind of weird. But we can combine both of those together, the Jn and the Jp, to get And you're only going to get one of those, right? Because we're going to only dope it with one of those. But you're going to combine both of those together, or do something to that. Let's do just the example that they have in the book. I'll make this window bigger. Maybe. We'll make this window bigger. We'll do the example they have in the book. And what they've done in the book is they've taken a pretty rudimentary example, and they've said the charge density for a p-type of material is equal to some p naught, so that's just some constant that they've set, e to the minus x over lp. LP is going to be a constant of this entire stuff, and so they gave some definitions of this. So at x is equal to 0, p0 was equal to 10 to the 16th per centimeters cubed. Remember, that's the units. And I'm writing too tiny, but we also have LP, the length of our, pretty sure that's the length of our thing, is equal to 1 micrometer. Okay, and they've given us dp is equal to 12 centimeters squared per second. And the cross-sectional area as well is equal to 100 square microns. Okay, and they want us to find IP with respect to this. And so we have to go back to some other relationships, but where we're going to start with this is JP is equal to minus dP, and then we have dP of x by dx, and they've given us an exponential, and so it's not a super difficult equation. And I'm looking at my board, and it looks really blurry and really small, so I'm going to bump up my font size just a little bit here. We end up with minus dP times q. Oops, let's back up. We're going to end up with a positive q dP over LP. Q. P0 is in there, e to the minus x over LP. We're just taking the derivative of this here. Okay? And what we know is that JP at 0 is equal to then Q dP, yeah, that's getting worse, dP over LP times P0. And that's just saying x is equal to 0. And that gives us a place where we can start. We know that this was equal to 1.6, this number. Where was it? 1.6. Or sorry, we're going to come up with JP0 is equal to, yeah, charge of an electron. This is where I'm going to cruise over to MATLAB and do it there. Because it's going to be easier to do it over here than by hand. You're going to actually be able to read what I'm going to type here. And so what we have is Q is equal to, what we have that saved from 4, and we can also go through and let P0 is equal to 10 to the 16. Let me see, LP is equal to 1 e minus 6 is a micron. DP is equal to 12. And let me see, A is equal to 100. Okay? And so when they went through this, they just did Q times dP over LP times P0. And that gives us 19,200. Drop my microphone again, sorry. That gives us 19,200, but we have some unit conversion mistakes with this. the 100 microns, and we had 12 centimeters squared per second. And so what that means is, how do we get from centimeters? What's the ratio from centimeters to microns, or microns to centimeters? And this is where we're all going to get in trouble with this entire thing. So we have to go through and look at actual units of that. So charge stays the same. The 12, let me see, the dP is 12. The units are centimeters squared per second. LP is equal to micron. And so I have to convert the micron into centimeters. And that sounds like it is 10,000 away. And that gives me 1.92 amps per centimeter squared. Okay? So units are going to, when you do cancellation of units on this, you have to make sure that we do it right. The 12 centimeters per 1 micron is the thing that would have screwed you up on this. And that's where we do end up with units of per centimeter squared. So be really careful about that. We also have the per centimeter cubed and the P0. Okay? And so best just convert all to centimeters and do that. So that's what's going to get us into the most trouble on this. Now, did we divide by 10,000 or multiply by 10,000? And the answer is yes. Well, the answer is you have to do cancellation of units. That would be a different lecture. So that is diffusion current.